In order to understand how to properly use a CPU, I need to go a little bit back in time and explain a little the history of CPUs. So I made a very, let's say, very simplified slide about the history of CPUs. They get bigger and they get faster, or at least they used to get faster. You can see that here I just roughly framed it from 75 to 2005, and so pretty much the same kind of concept still applied all across the way until 2005 roughly. So same thing, you have one CPU, but it just can do more things and can do them faster. For the ones of you who were around at the beginning of the personal computer revolution, you know that the first chips were running at like 1 megahertz, 2 megahertz, 3 megahertz, and these days you have 3 gigahertz, so that's like 1,000 times faster. And so what happened in 2005? Well, I guess that a lot more of you were around in 2005, and probably a lot of you bought a console around 2005, 2006. That's the generation of the PlayStation 3 and Xbox 360, and these were the first consoles, first mainstream consoles that used multiple CPUs. So the reason is simply that there is some sort of physical limit above which we cannot go. There's no... I mean, you cannot scale the frequency of a CPU indefinitely. You will just hit some sort of limit in terms of how fast electricity can flow, how much heat you can generate, how much power you can use, and so on. But we still need more powerful chips, so we simply put several chips in the same package instead of having faster chips. And so that's the big thing these days. If you want to use properly your CPU, you just need to do several things at the same time. So when you design a game, you might say, okay, my sound engine is going to run on a separate thread, on a separate part of the CPU, my physics engine on a separate part, and so on. And then you sort of break your game into smaller components by hand. But the problem is that this amount of CPUs, this amount of cores, keep on increasing. And if you do all that dispatching by hand, that's just going to become a problem which is more and more complex and harder to deal with. So you just need a system that works with that. Now, that's not the only thing. You have another big issue with modern CPUs, which is a bit less obvious. But once again, I simplified it a bit. You have memory, you have the CPU, and you have a bottleneck between the two. So when you want to access stuff that you want to work on with your CPU, just accessing it and bringing it to your CPU to do something takes ages. And when I say ages, I mean several microseconds. It's awful. So the good thing is that, of course, the industry came up with some ways of mitigating this. And so they introduced the idea of cache, which is memory that sits between the main memory and the CPU. And this cache is much, much faster. So okay, we are in a better place. If we use the cache instead of using the main memory, things work well. But now there is a problem. There is a big problem or a small problem, depending on how you look at it, and this is the problem. So for the ones of you sitting on the front row and the ones of you who have pretty good eyesight, you might be able to spot the problem. The problem is on the right of the slide. The cache is there. So this is to scale. So I took like 16 gigabytes of memory, which is like representative of modern gaming rig. And I took 256K of level 2 cache, which is also representative of a modern CPU. And as you can see, well, you're not going to fit all your memory in there. It's extremely small, and so you just have to be clever about how you use that very, very small amount of very fast memory. So if you know the specs of your CPU by heart, you might say, oh, but my CPU has a lot more than 256K. But here I'm talking about the level 2 cache for one core, so something a bit specific. I don't have time to go into the details of why this one, but let's say that this is the one that matters the most in terms of performance these days. Good. Now, how do you do that? How do you use that cache properly? Okay, that's how it looks. You have the memory, you have the CPU, you have the cache in the middle, and inside the cache you have what's called cache lines. They are just little chunks of memory that you can use to mirror your main memory. So every time that you want to do something, or every time that your CPU wants to do something with the memory, accessing the memory is slow, the cache is fast, so it will just copy a little bit of memory inside the cache and then use it when it's there. So that's what happens. Wow. Modern technology. Okay. So that's what happens. You just load a little bit of memory into your cache, and then you start using it. Damn it. So you just load a piece of memory inside your cache, and then you work on it. Thing is that a cache line tends to be always of a fixed size. Typical these days is 64 bytes. Could be bigger, could be larger. The principle still applies that every time you load something from the cache, it's not just the one little thing you need. It's more than that. It's like a big scoop of memory that surrounds the thing that you actually need. And to take just a real-world analogy, it's a bit like opening a drawer. If you want to access something which is inside your drawer, even if it's just like a pencil or something like this, something which is just a fraction of the contents of the drawer, you still have to pull the whole drawer to you. So you still do that work, which is bringing a lot of stuff to you, and then you just use a piece of what's in there. So it's a little bit annoying because you have all this work which is potentially wasted because you got all these things and you only use a piece of it. So how could you... Yeah, perfect, thanks. So you just load a small piece of your cache line and you do something with it. But then the good way of organizing your drawer, to keep with this analogy, would be to put in the same drawer the things that you usually need together. So when you open the drawer, not only you have the thing that you need immediately, but you also have the things that you will need right after. So you don't have to open different drawers and keep doing that. You just have one, and then you can process all the things which are in there. And the same thing works very well with a cache, because loading that cache line is slow. But then pulling things from the cache into the CPU is fast. And so if you can keep going with that same cache line, all these things here are free. Free, well, almost 25 times faster on average. So free. And then you need the next cache line because you keep going. All right, you pull the cache line, slow. Then you keep going, fast. And then it will be slow again. So that's already a lot better than directly accessing the memory. Like you pay the price every once in a while, and then you can use all the things that you have. But it's still annoying, because that memory is really slow. Or let's say the communication line between the two is very slow. And now, there comes the very, very useful part of it, and it's called a prefetcher. And the prefetcher is just something that looks at your CPU, that looks at what you're doing with the memory, and tries to figure out how it could help. Back again with my example with the drawers. If you're opening all the drawers, and you have someone watching you, eager to help, and this person notices that you're opening all the drawers in order. So you start with the first one, the second one, the third one, the fourth one, and so on. Well, that person looking at you is like, it looks like he's opening all the drawers in order, so maybe I can help by already opening the next drawers that he's about to need. That's exactly what the prefetcher does. It looks at your CPU and says, oh, I see where this one is going, just reading the memory in a very linear fashion, so I can anticipate this, and I can already start loading stuff into my cache. And by the time that the CPU will need the stuff which is in the cache, by the time the CPU will need the things which are in the next cache lines, in the next pieces of memory, well, it's already there. It has been loaded in advance, and you end up never paying that crazy high cost. You still pay it every once in a while, because the prefetcher cannot anticipate everything. But if he gets it right most of the time, well, most of the time it's free. And when it's not free, it's called cache miss, and well, it's expensive, but as long as it doesn't happen too often, you are fine. And that's pretty much all it is about. Data-oriented design is about being cache-friendly. It's about organizing the stuff in memory in a linear fashion, so that when you process stuff, the cache can figure out what you're doing and can help you. And this way, you use that fast memory and not the slow one. even though the slow one is like your backing store for the rest. Good. Now, where is the problem exactly? Why don't we do it this way? Well, let's take another real-world example. Let's take just a chair, and I conveniently have one there if you need a reference. And let's imagine that you're working on some, I don't know, first-person shooter, and then you have a chair, which is just a piece of furniture in one of your levels. And you need to represent that chair inside your code, inside your game somehow. And you ask yourself, okay, what is a chair? What do I need to store in there? If you're using Unity, you have a game object, and then you will start adding components to it. And what kind of components would you like to have? Okay, we need obviously a renderer, because we need to display that chair. So you need something with the texture, the mesh, the shader, whatnot. Good. What else? Oh, we need physics. We want to push the chair around, maybe break it. So we need some sort of rigid body representation of it. Good. This has nothing to do with rendering, but we need it as well. So it's also part of our logical chair. Let's keep going. Some AI. Well, the chair itself does not have much of an AI. But you might still have the need for your NPCs to, I don't know, walk around the chair, maybe sit on it, maybe pick it up and throw it at you, why not? A LOT controller, why not? Like if the chair is far enough from you, you don't want to render it with all the details and with a super detailed shader and whatever. So you just want to have some sort of logic that figures out how far it is and how much detail you want. That's also the kind of concept that you have to store inside your chair. Sound? Yeah, if the chair breaks or if you push it around. And I could keep going for a while, adding more and more components of your chair, depending on how much detail you want to have in your game. But the point stands that your chair, your logical chair, is a collection of different aspects. And all of these aspects might not have that much in common with each other. Maybe you still need some sort of interaction between the renderer and the physics, let's say, because the physics will tell you where your chair is, and the renderer needs to know where the chair is to render it. But it's really rare that you will need to deal with all these concepts at once. You just need one or two at the same time and so on. Good. Now you have a lot more than chairs in your games. You have characters, you have whatnot. But the idea is that if you can design just your one logical entity, a chair, and you need plenty of chairs in your level, you will just copy-paste it around or instantiate it if your chair is a class and you're programming. And so you will have plenty of copies of this thing. And this is what it looks like when you load your chair in memory and you want to work with it. So that's again a bit of a simplification, but that's roughly the idea. That you pull everything which is related to your chair, put it in the cache, and then start working on it. But maybe you just need to, let's say, do some culling on the chair. In other words, you want to figure out if the chair is in front of the camera or outside. So you can discard it or keep it for the renderer. And to figure out if the chair is in the view, you need to know where the chair is or how big it is. So you just need a few aspects of the chair. Let's say that this is the bounding box of the sphere, of the chair. Just the bounding box of the chair, just 2 points. Just one small amount of data out of everything that makes your chair. But this is what you've just done. You've loaded a bunch of things from memory, and you're just using a very tiny bit of it, which is completely wasteful, because once again, the blue lines are expensive. I know you have plenty of things in your game, and in all these things, you have that tiny bit that you need to do the culling in this example, which are in different locations, but which are part of all your logical objects all over the place. And all these logical objects might also end up stored in different locations in memory. And remember that prefetcher, which is looking at what the CPU is doing and can sort of reason about it and say, oh, okay, it's doing these things in order, so I can figure out what it will need right after. If you have something like this, and the little bits that you need are all over the place without any kind of structure, the prefetcher looks at what your CPU is doing and is like, what the hell? it cannot do anything to really help, and you end up having cache misses all the time and paying that high price of loading stuff in memory all the time. So how can we do this better? And actually doing it better is doing it in a way that feels a lot less structured. Let's just put all the things that have the same internal structure together. But then we sort of completely lose the concept of what is a chair, what is a character, what is, I don't know, any kind of element that you might have in your game. And we just store everything inside tables. That's a database. If you look at all the companies which are dealing with a very large amount of data, I don't know, Facebook, Google, whatever, that's pretty much what they use, just databases. It's not like if you look at the representation that Facebook has for your own profile, it's not like you have this one thing, this one object, this one instance that contains everything about you. No, it's more like you're going to have a big table with all the posts of everyone, a big table with all the pictures of everyone, and so on. And then you just have some sort of link that says, oh, by the way, this person owns these and these and these photos, these and these and these posts, and so on. And so what defines the logical entity of a person is just a link of different elements in these tables. And the same can be applied to a game. And the same could be applied, for example, to our chair here. And we could say that, all right, my chair is actually the combination of this render, this rigid body, this AI representation, and so on. And so what's good about this is that when you want to do that, once again, this culling, you want to know where all the chairs in your game and all the objects, regardless of their actual type, all the objects of your game, where they are, how big they are, and so on, if they are in front of the camera or not. Well, you don't need to know that one is a chair, one is a character, one is this, one is that. You just need to look at this list of bounding boxes, at this list of positions and extents of the box, and you can just look at them as if they were in a table, as if they were one after each other, nicely stored linearly in memory, without paying attention at which object they really are. And by storing all your data this way, that's what you have. All the things you need together are stored together. And once again, the prefetcher can do a good job, and you're using your cache efficiently, and you're not wasting space, you're not wasting time, and so on. It's just very unintuitive to work this way, because we have all been taught at some point to think in terms of object-oriented design. So in terms of, okay, I have one logical entity, it's my chair, it's a combination of a bunch of aspects, and then if I want to have 10 chairs, I just copy that concept several times. But so structuring this differently, and if you want to have a different chair, well, it's a different combination. And if you want to have something that doesn't have all these things, maybe, oh yeah, I forgot, there was one last slide I forgot to put in that deck. But if you have something that doesn't have sound and that doesn't have AI, it's not a problem. You're just pointing to a few of the tables inside your database and not to all of them. And when Unity is working on what we call ECS, so once again, if you've been following last Unite, you might have heard of this. ECS is just a way of structuring all the data that the engine uses, all the data that your games use, in this way, into tables instead of just a collection of object instances. And by doing it this way, we just guarantee that whatever CPU you have, whatever GPU you have, we are just using everything that it can do and not wasting its potential.